All right. Thanks everybody for joining us for the Using SPADE and Data Transformation Tools in FCS Express 6 webinar. Today we have Allison Irvine from Novo Software and Andrea Valle from Novo Software to give us a presentation and a background on the SPADE algorithm, how it's implemented within FCS Express, and how you can use that practically in the software for working with your own data. So without further ado, I'm going to turn the presentation over to Allison Irvine. She's going to start off today by giving us a kind of more thorough background on SPADE and the algorithm itself and the kind of considerations you're going to need for working with these tools. So thanks for joining us today, Allison. We'll let you take it from here.
Hi. Okay, so I'm going to begin with just kind of a general, like, this is what we're trying to do. So the purpose of SPADE is as an exploratory data analysis tool. So this is not necessarily meant to give you answers right away, like a yes or no, or a this is this cell population or that. It's really for you to examine your data in a different way. So this is useful because it simplifies your data. Your data typically has lots and lots of cells, could have lots and lots of different fluorescence channels that got measured. So when you take all this data, we want to, highlight the structure of the data, meaning where the cells tend to end up in the data space. We want to see if there's natural separation of the data in the groups. We want to see patterns that you can't easily see by looking at dot plots. So SPADE does a few things to simplify your data. This image up here is from the original SPADE paper. So before I get into this, I would just note that they've taken high dimensional, many cell data, and they've put it into this graph. And what they've done is, they've basically rearranged their data into this graph. Someone circled this population up here. In that paper, this was done manually, so it's a manual annotation. But there's an advantage, of course, over doing this over many dot plots because you can basically just look at one plot, and it's highlighting some of these differences using the colors and the placement of these little circles here to help you show that there is like a distinct population over here that's meaningful. So SPADE, when you get down into the actual implementation of it, it's a visualization and a clustering tool, both. So it does two basic things. We cluster the data into groups based on their location in your data space. So, based on like your dot plots, for example. And that reduces the effective number of data points that you're looking at. It also reduces the dimensionality of the clusters. So instead of looking at 30 dimensions in this plot up here, we're looking at 2, which is just the X and Y coordinates of where these circles are plotted. So as I just mentioned, classifying the clusters. So classification is distinctly means assigning meaning to groups of data points. So that was done manually in the original paper. I'll talk more at the very, very end about the distinction between classification and clustering. So the method used to cluster the data, this is important, because SPADE is more of a framework. So the method used to cluster the data assumes a particular structure of these populations of cells. Kmeans assumes that the clusters are spheres. Agglomerative clustering, which was used in the original SPADE paper, but they've now switched to Kmeans, so I think you have the choice between the two. Not in FCS Express, but sometimes like in the standalone SPADE software, they offer it, but agglomerative clustering, they switched for a reason. Agglomerative clustering, it doesn't assume a specific shape of clusters, but it does have a random element in forming the clusters. Basically, the clusters can be any shape. But I'll talk more about this in a minute when we get to clustering. So the basic steps of SPADE is downsample, cluster, visualize your clusters in a graph, calculate statistics of the clusters, and visualize those. So another image from the paper. So this is the original data. This is the data after downsampling. And then this is how they've separated this data into clusters. This is the visualization of those clusters in a graph. And then this is where they've calculated statistics of the clusters to create these colors, to get these colors and size the nodes as well. And then the circles are manual annotation. So I'm going to get started on these 4 steps. Yes. In general, downsampling is basically just throwing away some of your cells. It's saying that I've got so many hundreds of thousands of cells, millions of cells. I don't really need all of them in order to see what's important in my data, to see the overall patterns that are happening in these cells, so I can get rid of some of them. So the question of how to get rid of them determines what kind of sampling you're going to use. There's lots of different kinds of downsampling. Simple random sampling, which is used in TISNI, and it's the one that you most often see. Interval sampling, stratified sampling, which is used in citrus, and density-dependent downsampling, which is used in SPADE, and it's one of, I think, the neat and good and useful features of SPADE. So a little bit more on that. So simple random sampling is defined basically by its name. Oh, sorry. So you just randomly select some number of data points from your data set and you keep those. So you've got 1,000 cells, you want to keep 100. Okay, so you randomly choose 100 cells, those are the ones you keep. You continue doing your analysis on those and you throw out the rest. Interval sampling just means that, you know, you would keep every nth data point, like the first one, the 5th one, the 10th one. And if the data is in random order, it's just the same thing as simple random sampling. It would make more sense if you were doing like some kind of time analysis. So the effect of this is that you would have a smaller data set. The distribution of the points would be, it should be about the same as the original. So by distribution, I mean like how tightly packed these data points are. So I've made some sample data here. So this group of data points are very tightly packed, and this one's less dense and this one's less dense. So when you randomly sample, you're going to end up with these populations having the same kind of relative density to each other. Now, density-dependent downsampling does some tricks to achieve a different goal. So the goal in density-dependent downsampling is not to maintain this relative density between populations. What they actually want to do is say we actually want all of the populations in the data to have roughly the same compactness and density of points. So that's what the target density and the minimum density is used for. Well, that's what the target density is used for. The minimum density is actually more for ignoring outliers. So we'd say, okay, if it's you know, a few data points floating around on their own, we're going to get rid of those. But the target density is saying that, well, actually, this is a good example right here. Let's say that's like our target density. So we're going to try to get these two populations to have the same density. So there's a few technicalities about how the target density is calculated. It's basically based on neighboring data points to each data point. So our density is defined as the compactness of clusters. So we look at each data point and we say, okay, how many data points are within some radius of that data point? That's the density of the data point. We want to keep that uniform over the data space. So the purpose of this is basically to make sure that if you've got different populations of cells in your data set that you won't lose them or have them, you know, you want to highlight all the populations of data in your data set, even if they're more rare than the others. And you don't want the super populous groups of cells, like the super dense populations, you don't want those to just like dominate your analysis and to have that be the only thing that you focus on. So the next step is clustering. Clustering is another way of effectively reducing the number of data points. Although what you're doing now is you're basically getting rid of all your data points after you've assigned them to groups. And all you need now is just information about the groups. You don't need the actual cell values. So you can use, for example, like the average value of this group of cells, the average B red A, the average D blue A value, and that's all you would need to describe this cluster. So what we use is Kmeans, and it's a pretty commonly found clustering algorithm. We have it used, we have it available separately in the software, and it is there's another presentation on it that gets more into detail about like the actual steps of the algorithm and everything. It's the cluster analysis and data transformation presentation. But in basic words, you specify some number of clusters. K-means partitions the data into that many groups based on Euclidean distance. But the important things to note about this is that because K-means uses Euclidean distance to measure the distance of points to each other, it is effective on spherical data because the Euclidean distance is the same in all directions. It does not perform well when the populations are non-spherical. And because of this, it's usually used as a pre-processing step, and in SPADE we're using it as a intermediate step, and we're over clustering. So, okay, well, I'll show the image later. So even though we may know that there's 5 populations in our data set, we're going to use 100 clusters to cluster the data because those populations are oddly shaped. It might be shaped like a pyramid or skewed, and what we're trying to do is use a bunch of small circles to form that shape. So presumably if you overcluster and you separate your data into many small circles, once you combine them you will be able to reform the shape of the entire actual population. Here's a quick intro to node edge graphs. So this is the actual method we use to visualize the clusters. So a node edge graph, it's used for different kinds of analysis. It's used for a lot of, for analyzing networks a lot of the time. It's used for analyzing relationships between objects. So a node is a circle. An edge is the connection between the two objects. And a weight is a value that describes the strength or the length of an edge. The weight of an edge is got a very open meaning. It could be a distance, which is how we're using it in SPADE. It could be, but it could also be something like a cost. If you have, if these are actual locations on a map, for example, and these are paths between the different locations on a map, this could be something like, how difficult it is to get from one place to the other. Sorry, that keeps happening. So a minimum spanning tree takes this concept of the nodes, the edges, and the weights, and is somewhat of a simplification of it. So you know, what we want to do is find a way to connect all of these nodes with the least cost or the least distance or weight of all these edges. So we just remove edges one by one until we still have all the nodes connected, but this the total weight of all these edges is minimum. So this connects to visualizing clusters in this way. So what we do is after we've clustered our data, we've got this collection of our cluster averages, the average of all the cells in each cluster. So we form a graph by saying that each cluster is a node, and the distance between the means of all the clusters is our edge weight. And so what we do, we form a graph just like this one, where each of these is a cluster and all the nodes are connected to each other. There would be an extra edge there. And then we form a minimum spanning tree. So what this effectively does is it connects all the clusters that we found, but we connect the clusters that are closer to each other, and the clusters that are further away from each other don't have a line between them. And that's how we represent the structure of our data. An important thing to note is that in the concept of a node edge graph, the only thing that's important is the nodes and the fact that there's an edge between them. The actual way that these nodes are laid out on a graph, the way that they're plotted, like their locations, it's actually arbitrary. There are many visualization algorithms that are used to place these nodes in a way that is visually appealing and allows you to see all of them. But you could rearrange these nodes in any way that you want, as long as the same edges connect them. It has the same meaning. So there's this concept of upsampling that's introduced by SPADE as well. So this is what we do at the very end when we want to calculate statistics. So we've already got our graph, we've got our minimum spanning tree. Now we need to create different sizes for the nodes, and we need to maybe calculate the colors that we want for the nodes. But we want these statistics to be based on the entire original data set and not just our downsampled data set. So that's the purpose of upsampling, is to help us achieve this. So we go back to all the cells that were not downsampled at the very beginning, and we say, okay, well, which cluster would these cells have belonged to if we had selected them and clustered them and gone through all this? So we, in the original data space, we look at all of our cells that were not sampled, and we say which cluster they're closest to in the original data space. We assign them to that cluster, and now we can calculate the statistics for each of those clusters based on the entire data set. So we end up with a SPADE plot at the end. Now this is one from FCS Express. So the nodes are sized according to the number of cells in the cluster. The colors are based on some statistic like the median value of particular fluorescence. And here's a little screenshot of the options that we have. So you'll see some of the things that I was talking about earlier with downsampling here. So what we've got is, here's our overall transformations tree. So this is going to show all your transformations. This is the details, the options specifically for SPADE. These are the parameters that you want to use for SPADE in the data set. And this is just data scaling over here for the individual parameters before you send it to be analyzed by SPADE. Here's a close-up of the options for SPADE. All right, so we've got the density-dependent downsampling parameters over here on the left side. So there's two ways that you can control your downsampling. You can specify a sample size. You can also specify the min density and the target density. So this checkbox just controls which one you want to use. If you select sample size, we will automatically calculate the target density and minimum density so that you will end up with that number of cells. If you specify min density and target density, the number of cells you get depends on this. So the target density, again, is going to control the desired density of the populations that you want to keep. The min density is going to help you exclude things that you consider outliers. Over here we have the Kmeans parameters. So number of clusters that you want to cluster, the maximum iterations for Kmeans. More than 100 is usually not necessary, as a side note. Minimum % of cells per cluster, just to help you make sure that your clusters aren't too small. And this is the gate. This is something that you see in all the other transformations, and the auto calc button. So check to automatically recalculate, uncheck to not, instead to use this button to recalculate. Okay, so here's a little recap. We've got our major steps, which is density-dependent downsampling, to achieve the goal of having the same density for all the populations you want to keep. Clustering, to simplify the data further, and to represent groups of cells just with the average of them. The minimum spanning tree, which is to connect all those clusters as nodes in a graph and visualize them so that the clusters that are closer together are connected with an edge. You want to visualize the minimum spanning tree using a visualization algorithm to lay out these nodes on a 2D plot. And then you want upsampling to take your unsampled data and go back and assign them to the clusters so that you can now calculate statistics based on your entire data set. So some of the advantages and disadvantages of SPADE. The density-dependent downsampling is definitely a plus. It's an advantage. It helps keep from very dense populations from dominating your analysis. And it also helps to highlight less dense populations that may still be meaningful to you. When you construct the minimum spanning tree, you're learning the underlying structure of your entire data space effectively. So you get to reduce the dimensionality of your data effectively and reduce the number of data points. Some disadvantages have more to do with the specific clustering methods that you choose. Theoretically, you could use any kind of clustering for that clustering step in SPADE. But each clustering algorithm has its own advantages and disadvantages. If the shapes of the clusters are not easily modeled by spheres, for example, or by the clustering algorithm that you chose, you might have to increase the number of clusters in order to get the detail in the shape of the cluster you're trying to model. The upsampling process uses Euclidean distance, so that's just something to keep in mind. It's very similar to the advantages and disadvantages of K-means clustering. So the way that your data gets mapped to clusters at the end, it's going to go to whichever cluster is closest in Euclidean space. But you know, if your populations have weird shapes, there may be problems. And Another thing to remember is that the minimum spanning tree construction, it's an optimization. That process is an optimization. And if there's differences, even small ones, in your data value, your minimum spanning tree could look completely different each time. You should still see the same major structures in the minimum spanning tree, but it would be very difficult to get the exact same layout every time. So comparing trees can be difficult if the trees are from different data files, for example. And I'm going to pass the presentation back over to Andrea so he can talk a little bit more about using this in FCS Express.
Great. Great. So we're going to make Andrea the presenter here. And while we do that, if anybody has any questions about the presentation from Allison thus far, please feel free to enter your questions into the questions and answers box in the webinar meeting panel, and we'll try and come back to those at the end. So thanks again, Allison, and here's Andrea.
So thanks. I hope you can see my screen and you can hear me. We are now going to see how you can run SPADE on your file directly within FCS Express. So as you can see here, I have a very simple layout. Actually, your layout can be as complex as you want. I have just a single plot with a single gate, and what I'm going to do is to run a SPADE specifically on the events that are within this gate of interest that I've called it cell of interest. So the first thing that you need to do is to go in the Tools tab and open the transformation dialog. As all the other dialog in FCS Express, the transformation dialog can be resized, can be moved around, and can also be docked on one side of your screen. To create a new SPADE transformation, you can click on this drop-down menu and just select SPADE. You can either keep the default name or you can change it. And you see here the SPADE dialog. And we are now going to see all the options. The first field that you need to fill is the template file. And the software needs a template file in order to retrieve the list of parameters. In this case, since I already have a file loaded in the layout, that file has been selected automatically here as a template file. If you're starting with an empty layout, or if you have multiple files opened in your layout and you don't want to use the one that FCS Express selects automatically, you can simply click on this ellipse and navigate into your PC and grab any other FCS file. You see here the list that was retrieved from this file. I'm going to select a couple of parameters on which I want to use on my SPADE transformation. You can just click on the checkbox. And one of the new features that we have in this latest release of FCS Express is the ability to select for each parameter a scaling option. And you see this option at the bottom of the SPADE dialog. You see as soon as you click on a parameter, you can select the scaling. In this case, the automatic it's checked on, so the B exponential scale will be used. If you don't like this scale, you can just uncheck this checkbox and select one of the other scaling options that are available in FCS Express. You can do this parameter by parameter. The next option that you may want to use is the gate option. As I mentioned, I'm going to run SPADE on the cells of interest gate, so I will select this gate here. And then we have three options, as Alison already told us, that are referring to the Kmeans clustering step of the SPADE algorithm. You see the number of cluster, maximum number of iteration, minimum percent of cell per cluster. I will keep the maximum number of iteration, the minimum percent cell per cluster as they are. I will just reduce a little bit the number of cluster. Probably 50 is enough in this case because we are dealing with very few parameters. So I think this it's more than enough. Of course, you can increase it or you can keep at 100. It's just up to you. The next group of options are referring to the downsampling step of the SPADE algorithm. You see, as Alison already mentioned, you can either specify the density percentile, you see here the minimum density, and the target density. If you do not want to specify these values, you can uncheck this option. You see that these two values will be hidden, and you can specify the sample size. So FCS Express will take care of calculating the minimum and the target density based on the value that you insert in the sample size. Last but not least, the automatically calculate SPADE option. This is flagged by default. This means that every time that you change a parameter, that you change a scale, or that you change any option here, SPADE will be recalculated. And this is usually fine, but if you are dealing with very large data set, you may want to uncheck this, then to change all the options that you want, and then when you have done, just click on Calculate SPADE. Now we are dealing with a quite simple file, so we can keep it on. So now the SPADE transformation is ready to be used. And how can you access the SPADE tree in FCS Express? You can do it by inserting from the Insert tab what we call heatmap plot. You see now the heatmap, the FCS Express is telling us that the transformation is still not applied, so the heatmap will be empty, so we can click on Continue. You see it's not applied, also the gate cannot be calculated because we don't have any transformation here. And how can you apply the transformation to the plot? Well, you can simply drag and drop the transformation on top of your heatmap. And very quickly, the SPADE tree will be calculated and plotted in your heatmap plot. So you see here we have 50 nodes, and this is because we decided to calculate 50 clusters. You see all the edges, and you see that each node is actually colored based on a statistic. And in this case, you can see the statistic which is used to calculate the color on the y-axis. You see now the statistic is the arithmetic mean of the time parameter, which is not super useful in this case, but it's by default the first parameter when you open an heatmap. But you can simply change it to be, I don't know, CD4, for example. Now the color is based on the arithmetic mean of the CD4P cycle 7. And you see that we have here a nice group of 4 nodes that are red colored. This means that they contain events that have a high arithmetic mean for CD4. So they will probably be CD4 positive cells. I'm not sure you can appreciate here, but I see some barely red nodes. So this will probably be cells that express lower amount of CD4. Let's have a look at something else. For example, CD18, you see here 3 nice nodes, and CD8, you can see here 5 nodes that contains CD8 positive cells. The x-axis is fixed, so it just, let's say, a second title. I would like to mention a few customization that you can use to personalize your heatmap plot, exactly as you would do with any other object in FCS Express, and exactly as you would do in PowerPoint. When you want to, sorry, I hope now you can see me, hear me better. When you want to format an object in PowerPoint or in FCS Express, you can simply right-click and select Format. You see we have a bunch of different options here on the left of this dialog. You see you can change the background, you can change the border, and I will just show you a couple of options that may be useful for customization. You see here in the overlay category, you have the parameter that is used to color each node, which is actually the same that you have on the y-axis. Then you have the statistic. You see here CD8 arithmetic mean, which is exactly the same. So you can change it here or on the y-axis. Here you can also change the statistic. Let's click on preview. Now we are coloring events nodes, based on the CD4P cyclone 7 median. Then you have the ability to apply a gate on your plot. You may want to apply the cells of interest. We are going to do it in a few minutes. And last but not least, you can customize your SPADE tree not only regarding the color, but also regarding the radius of your nodes. So you see, by default, no radius parameter is selected. You can select any other parameter, for example, I don't know, CD4, and you can pick up a statistic. Actually, you can also select the number of events. In this case, the parameter that you have selected here doesn't matter. You can select any of the available parameter if you want to design the radius based on the number of events. I will click on preview, and now you see that the radius of events tells you, gives you an idea of how many events there are within each node. For example, you see that we have some very large nodes here. They will probably contain a lot of events, and very small nodes in the rest of the tree. Let me restore it, and let me show you another option that you can use to customize your heat map. Under the heat map category, color level subcategory, you see you can change the color level. By default, it's green to red, so low value are colored with green, high value are colored with red, and intermediate value are black. And you can also change the style. So for example, let's play a little bit. If you change the color level to be red gradient, you see this is the results. You can change it green to blue. This is the results. So you can pick up the one that better fit your need. It's just a matter of color. And then you can also change the style. In this case, it's mean plus or minus standard deviation. You can change it to be percentile, for example. You see now we have some very bright red nodes here, but we have some a little bit darker nodes here, but they are still red. And then we have all the shade of black and green. Just remember, green means low value, red means high value. Last but not least, the last option that I want to mention is the legend. You can just click on visible and you can put it wherever you want, for example, at the bottom. And you see now you have the shade with the value. Again, low value green, high value red. I will just restore to the standard. So what you want to do now is probably to create some gate. So for example, what about if you want to analyze further, I mean to create some downstream analysis on the CD8 positive nodes? You can create gate on your SPADE tree by going into the gating tab and by selecting the well gate. Just click and drag and drop to highlight the nodes that you want to include in your gate. As soon as you will release the mouse button, you see that the create new gate dialog will appear. You will be able to set a name. I call the gate CD8 because we are gating on CD8 positive nodes. You can change the color if you want and click OK. Once you click OK, you see that you still have a dialog here. So the software is still in a standby mode, and this allows you to further select other nodes. You can just press Ctrl on your keyboards and select multiple nodes to add to your gate or to just deselect them, you see. When you have done, you can just click on Close. Let's do the same for CD4. So let's change the parameter used to color the nodes to CD4. Select well gate, drag and drop, give a name, a color, and that's it. So by default, gates are not displayed on the heat map, but you can always right click and select show gate. You can select either one of the other, or you can simply select all of them. And you see that now the CD4 and the CD8 gate are displayed as a border on the selected nodes. Always remember that you can keep track of your gating hierarchy by opening the gate view. You see here we have the cell of interest gate, the CD8, and the CD4. So what about if you want now to further investigate the cells within those gates, for example, with a back gate, to see how they looks like. Let me zoom out a little bit. What you may want to open is, for example, a core dot plot. You can pick it from the Insert tab in the ribbon bar. Click on core dot plot, click on your layout. By default, the first two parameters are open. You see the time here and the forward scatter high in this case. Let's change to be, for example, CD4 and CD3. And you may want to apply the cells of interest gate. So just drag and drop the gate from the gate view on top of the core dot plot. And you may see here that the green gate that was supposed to contain CD4 cells actually contains CD4 cells. The red gate actually contains CD8 cells. Someone of you may also have noticed that you have here some CD4 low population, and those are the ones that I was referring before. So I'm not sure you can see them, but you have some a little bit darker red nodes here. So they are darker because they are not bright in terms of CD4 as the CD4 T cells. If you want to retrieve statistic from this plot, you can simply right-click and select statistic. This is the standard statistic table. You can always add or remove statistic from any kind of table like this one just by right-click. You see you can uncheck or check statistic. In this case, for example, I will remove the file name to make this a little bit smaller. And you see that for the CD8, for the CD4, you have the percentage of gated cells, percentage of full cells, number of events, and so on. But as you can see, we have a lot of statistics available. And please remember that those gates have been created based on those nodes, and so based on the clustering that SPADE perform. Another nice way in which you can deal with statistics is by opening the spreadsheet, which is one of the new features that we introduce in FCS Express version 6. And you can insert the spreadsheet here in the Insert tab. So this works more or less as Excel's. I'm not going into any details, just consider that we have a lot of resources on our website, but anyway, if you have some doubts, please just ask. Let's say that you want to insert a column with the subset, a column with the percentage of gated cells, and you want to insert here the CD8 and the CD4. How can you fill this spreadsheet? Well, as often happens in FCS Express, you can simply select what you are interested in and drag and drop. And you see that now we have the two statistics in the spreadsheet. And the beauty of the spreadsheet is that you can, for example, create formula. This is just a very easy example with the sum, but you can really create whatever you want. You see here we have the formula tab with a lot of formula. I will show you that you can also retrieve statistics directly from the SPADE tree. So up to now we retrieve statistics from this plot, actually from this table. I will delete this. If you want to retrieve statistics from this plot, you can right-click on a cells, select Insert Token. What we want is a statistic. Here in the data source, you can select the plot that you are interested in. In this case, we are going to select the heat map. And in the statistic category, we are not actually interested in the heat map statistics. You see that those statistics are referring for specific and single wells. What we want is a 2D statistic. We are interested in the CD8 gate and in the percentage of gated cells. Let's click OK. If you want to add the CD4 statistic, you can do the same. So right-click, Insert Token, or you can simply drag and drop these cells to fill the cells below. Now we have an exact copy of the cells below, but you can always right-click, of the cells above. You can always right-click and Format Token. You see that the advantage of doing this is that the data source is already selected, the 2D statistic is already selected, the statistic, the gated cells, is already selected. What you just need to do is to change the gate and click OK. Some of you may have noticed that the statistic that I've inserted here are not equal to the one that I have in this table. Actually, if you see, these statistics are actually referring to the percentage of all cells. And this is because before we had 3 statistics from this plot, and actually this plot was already gated on the cells of interest, while our heat map is still ungated. So in this case, what you may want to do is to simply apply the gate on this heat map, and now you see that the statistics are referring to the cells of interest gate, exactly as the previous statistic we're doing. So just a brief summary. We saw how you can create a new SPADE transformation, how you can insert an heat map via the ribbon bar. You can apply the SPADE transformation simply by drag and drop the transformation on the heat map. We saw how you can create well gate to gate multiple nodes, and how you can back gate those gates on a standard color dot plot. We also saw how you can retrieve statistics either from a standard dot plot or from the heat map, and how you can use the spreadsheet if you want to play around with those statistics. What we didn't see yet is how you can perform and run a SPADE on multiple samples. Because think about when you want to compare multiple samples using SPADE. Well, you have to know that if you run SPADE on 2 different samples, you will end up with 2 different 3. So it will be hard to compare 2, 3 deriving from 2 different samples. So what you need to do in this case is to merge the file that you want to compare into a single FCS file. And this is exactly what I've done here. So here on the top left of the screen, you can see that I have this sample. You can see also by the title, I obtained this sample by merging 8 different files. Actually, you can still not see that they are 8, but I will show you in a moment. So this sample it's the resulting of a merge. Actually, when you merge different files, you are actually concatenating them one after the other. And you can do that by going into the Data tab and by selecting the Batch Export features. Again, we don't have time now to go into any detail. We have a quick video guide on our website. Just write us a note if you don't find it. That explain you in a couple of minutes how you can merge multiple FCS files together. And the advantage of FCS Express is that when you merge multiple files, you can create an additional parameter. You see here, it's called file identifier, that will allows you to further discriminate the file that you actually merged previously. So you see here you have different columns. This is file 1, this is file 2, this is file 3, and so on till file 8. This is because I have merged 8 files. And as you will see in a moment, since you will be able to gate on each of these columns, you will be able also to separate the file that you merged together. But let's come back. This is the merged file. I have run SPADE on all the files actually using this gate, and I have obtained this SPADE tree. I've opened different copy of the SPADE tree just to display different parameter. You see here I'm displaying CD19, here I'm displaying CD8, and these are the CD8 nodes. Here I'm displaying CD4, these are the CD4 nodes. These are the CD16, 56 nodes. Actually, in this SPADE tree, I've displayed all my 4 gates. You see green, blue, orange, and red. And here I've done exactly what I did before. So I've just backgate to see that the population were actually the one that I was expecting. You see CD19, CD3 positive, CD8 positive. Let's have a look at CD4. Here are the red one. And last but not least, CD16, 56 double stained cells, which are the orange one. But still, this is the SPADE tree with all the events, so with all the data. What I've done in this page was to create different gates to select all the 8 files, each single file within my merged file, and I've applied each of these gates, to a SPADE tree. You see here, this SPADE tree is gated on file 1, this SPADE tree is gated on file 2, and so on till file 8. So once you have the SPADE tree with each of different gate applied, you can also retrieve statistic. And in this case, if you retrieve statistic from this SPADE tree, those statistics will be referring to file 1. While if you retrieve statistic from this tree, those statistics will be referring to file 2. So I did exactly the same as I did before with the single file. I retrieved statistics from different population, you see here, CD4A19 and the double-stained CD1656 cells. I retrieved those statistics from all my file, you see 8 column. And also, since in my dataset I was dealing with 3 different experimental groups, I grouped the file together. So you see file 1 and 3 was actually belonging to the green group, then I have the blue group and the orange group. I mean, this is just an example, but just imagine what you can do with your dataset and with your experiment. Then I calculate the mean for each population and for each group, and also the standard deviation. And last but not least, I have created a nice bar plot summarizing all those results. So the take-home message here is that you can perform SPADE in FCS Express. You can do it quite easily. It's very fast, and even more important, you can integrate the SPADE analysis together with all the other features of FCS Express. You see color dot plot, you see the spreadsheet, you see the bar plot. So this is the real power of FCS Express. So it's really not only data analysis tool, but also a data reporting tool. So I think this is all. I would hand over to Sean to make a summary of what we saw till now.
Great, thanks Andrea for the presentation. And again, if you have any questions for Allison or Andrea or the team at Novo Software in general, please take a moment and type them into the questions and answers box. We're going to be getting to those questions in just a few minutes. But again, I wanted to kind of give a very high-level summary. I know we talked, I know Allison and Andrea talked in quite a lot of detail about the SPADE transformation and kind of how to use that practically in the software. But again, at a very kind of high level, you know, SPADE is a data exploration tool that's available within FCS Express. And we try and make this as easy to use and fully integrated as possible within the software. So that way, you know, you don't have to have some sort of kind of background in computational science or, you know, programming or R scripting to use these tools. They're really out of the box. You can come into the software. You can see, you know, as Andrea was kind of working with these, the interface is very kind of easy to understand. The other thing we should mention is, you know, we've primarily been showing flow cytometry data today, but the SPADE transformations and the other transformation tools that are available in FCS Express can be performed on image cytometry data or really any data files that are derived from a CSV file, since we allow the importing of CSV file data sets into the software. So those are some considerations for, you know, different data types that you may have. And as you saw kind of Andrea working with these tools in the software, you know, the SPADE trees and the heat maps and the other plots, they're all fully customizable, which really means that, you know, as you're working with these data sets, you are creating your report, you're creating your publication of all of your results in real time in the software. So you're not spending any kind of time taking that data sets and those visualizations out to some other software to create a figure. Really, you have it at your fingertips, and you saw kind of the speed of working with that in FCS Express. As you adjust, some of the kind of variables within the SPADE algorithm and the data transformation tools, depending on the sample size and how big the data files are, they're essentially updating for you in real time. So you're kind of getting that information very quickly and easily. Now, again, if you want to try any of this, if you haven't tried it yet, and you don't have version 6, you can get a free 30-day trial of the software at denovosoftware.com. So we encourage you to visit the website and kind of check that out if you haven't already. And if you have any questions after the webinar, or if you're viewing a recording of this webinar, you can email us at support@denovosoftware.com. Now with that, I do want to kind of flip over to Allison for one last kind of more in-depth summary about the SPADE algorithms and some of the limitations and considerations for working with your data. And we're going to flip that over to her right now for that. All right, Allison, so we're seeing your screen.
Sorry. Okay, I had to unmute myself. So I just wanted to kind of throw this in at the very end. This isn't really specific to SPADE, but it is something, it's like some information that I'm trying to spread around. For all you people out there that work with bioinformaticians and that are looking at new methods to use for your data, I want everyone to start thinking about these kinds of questions to ask yourself when you're having that conversation with your bioinformatician or you're exploring some new data analysis tool. So the first thing is, do you have training data? Do you have pre-classified data? If you have data that is classified already and you've just got new data and you're trying to analyze it exactly the same way, it might be a good idea to look at classification algorithms as opposed to data exploration tools. But you can only do that if you have training data. Next question is, how large is your data set? If you've got a very large data set, you might need to subsample before applying the algorithm. We've seen that before with SPADE and with TISNE. Especially with TISNE, because some algorithms use these things to look out for. If it's iterative or uses pairwise distances, you need to be really careful about using large data sets because it can take forever. Normalization data scaling. What are the shapes, what are the densities, and what are the sizes of the populations that you're looking for? Sometimes the same algorithm will be implemented with slight modifications. And sometimes the original algorithm is kind of inefficient, but maybe 5 years later someone came out with another slight modification to it that really improves it. So it's good to look for those. Limitations of the implementation that you're using. The same algorithm, such as TISNE, for example, will be implemented by many different people in many different kinds of software, and certain ones will be faster than others, certain ones will take more memory than others. It might not even be the programmer's fault, it could just be the particular programming language they're using. But sometimes it is the implementation, and sometimes certain implementations will have bugs and certain ones will not. So it's good to make sure that you're aware of the algorithm that you're trying to use, who's implemented it. And is the algorithm going to give the same results every time? So a lot of times you might see these words, a globally optimal result or a locally optimal result. So if you see the words locally optimal result or random initialization, which I probably should have put on here, then that means that if you run this algorithm on different data sets under different conditions, you will get results that vary quite a bit. And so you would want to do something like in the example Andrea just gave, where you merge data files and then you form a SPADE tree. So that way you can make sure that the results are going to be not, that you can compare the results from different data sets. So these are just some little take-home notes that are pertinent to any algorithm that you use. And it's good to ask these questions and to think of these things when you're reading some paper about some new method that someone's using. And that's all I had to say on that. So I was actually going to skip over to a question that I saw.
Yeah,
okay, Sean?
Yeah, and before we go there, again, thanks everybody for joining us on the webinar today, and we'll be answering questions in just a moment.